This is lecture number 30 of the course AU 203 Statistics and Quality Control. In this lecture, we are going to start a fresh topic of control charts. Before going into this control charts, we would like to go into what is process starts with, and focusing on the production process. We will understand what are the causes of variation in the production process. And then we will look into the types and sources of variation, and then we will define what is control chart and its nomenclature, and then we'll go into the general theory of the control charts, and then go into the benefits of control charts, and in the end we will go into the different types of control charts. So what is process? So process transforms input and output. So what does it mean by input and output? In this production setup, you have certain input. For example, you need to have some raw materials, you need to use your tools. So all these becomes your input. And your process is some sort of a black box which takes in certain input and transformed into output. So process is actually that black box which turns all the inputs into an output, and output is our product. So once we talk about a process, the efficacy of the process lies with what machines are used in the process, what the level of operators are used, what methods are used in the process, and under what environment this process is taking place. So all these are the factors which are responsible for turning the input into an output. Once we got an output, I mean, even this inspection can be done at the input stages, whether we are bringing in some quality material in, or we have some right tools available for the process. So whatever the inputs are, because what the inputs are, they are actually sort of a consumables. Once they get consumed, and in this way all this input transformed into an output. An output is could be our product in the production setup. Once we have an output of a product, and then we need to inspect through instruments, and we need to have some quality control procedures, and these instruments must be calibrated, and there is a skill set available for the inspector who is going to inspect the output. So this is what the process is, and you can think of output is depending upon an input, and the function would be called as a process. So process can be thought of as a function which transforms all the inputs into an output. So what we would say that this process, once you're talking about a process, it means you are dealing with 6 M's. 6M means you are dealing with the man, which is an operator, materials which you are bringing in as an input, the method which is required for a process to undertake, and the machines which are required to undertake the process, and this environment, what you call it, a mother nature. That would be the 4M, 5th M rather, and in the last M is a measurement. Whether the measurement takes place at an input stage, whether the measurement takes place during the transformation process, or whether the measurement takes place at the output stage. So in any process, all the time we are dealing with these 6 M's. So called man, materials, methods, machine, mother nature, and measurement. So in order to get a good product or a service, you need to look into these 6 M's so that your function is good enough to transform all the inputs into an output. If you look at your process, so whenever we talk about process, the word which comes into your head is it is some sort of a black box, which is a method, which is a function which transforms the input into an output. So you can think of your we already know about random variables. So random variables itself was a function taking certain input and transformed into an output. So every process is dealing with some variations. If you look at the process, what process is coming into the process is actually in all inputs. And these inputs it could be your material input, it could be the information input, it could be the skill level set of the operators, it could be the environment that is actually uh, uh, taking a role in bringing this input into an output and affecting the process, an environment and documentations and all these things would be I mean the records, what I call it, all this would be. And as we know, these inputs to be coming from somewhere, and we call that entity to be a suppliers. So it means all the quality of that input is depending upon the quality of the suppliers. If we have good suppliers, good vendors, so we could have a better input for this transformation process in which this all these using this input, your process turns all this input into an output. And in an output, it could be anything. It could be a product, it could be a service, or it could be some information, or it could be some documents that would be an output. So that depends upon the two factors. So one is actually called as the voice of the customer, and as you know, the output is given to the customers. So in order to produce a good output, you need to look into the behavior of the customers, what customer wants. So that is usually called as the voice of the customer. So for a process, in order to improve the product or a service which satisfy the needs of the customer, there is an input given to this process, and that is actually called as voice of the customer. At the same time, you are undertaking certain process, and whether your process is in control or not in control, and you are using statistical methods, what you call it SPC, statistical process control. So this is something we usually call it a voice of the process, and we will deal quite in detail about this statistical process control later. So in this overall big picture, you can think of what the process involves: suppliers, input and output, and the customer. So in short, we call it SIPOC. SIPOC means S for supplier, I for input, and O for output, P for process, and C for customer. So whenever you are interested in a good quality product or a service, you need to look into the aspects of suppliers from the supplier's point of view, from the process point of view, and from the customer's point of view. So all these ingredients would make the product a better quality product. Even though we haven't defined quality, we will go quite in detail in the later lectures. Okay, so as we have seen, this process is a function of inputs. If inputs are being varied, the output is going to vary. So once we look at the variability that is inherent in the process, for example, it could be one of the scenario in which A stands here for accuracy and P for precision. So once you look at this process one, in which you see this dispersion is small, so most of the data is central tendency of the data is much higher. So we can say that this is a process, even though it is not up to the target, so it is away from the target, so it is not an accurate process, but it is precise. So the precision refers with the variability that is inherent in the process, and the dispersion is a measure by which you can look into this variability. So this process one shows a lower variability, but the accuracy, it is lacking accuracy. Let's say if you have another process 2, where you can see the data points are all scattered, and so but there are several of them are trying towards the target. So but once we see there is a huge dispersion in that process, so the dispersion of the data is reflected through this precision. We already know the term bias. We have seen in this interval estimate and point estimate. So the bias here away from the variation from the target is much. So it means higher bias and less accuracy. Whereas precision is related with variability. So it has some large variability, so precision doesn't exist. But the targets, several of them have hit the target, so we can call it to be inaccurate. So all are in the circle everywhere, but there is a dispersion, higher dispersion. Or the process 3 could be in such a way that it is not actually towards the target, because half of the circle is without any dots, so it means it is away from the target, and at the same time the variation, which is a variation, means the dispersion or the standard deviation or variance is much higher in this process 3. So which is, we call it a neither accurate process, having a lot of bias there, and at the same time a lot of variability is there. Okay, and then another process for what you call it, which is accurate as well as precise. So most of the dispersion is much low, and the bias is also low. So that is something, an ideal case, which is accurate observation and precise observation. So for any process, whether a production process or whether whatever a service process or whatever the process is, there is a variability present in terms of accuracy or in terms of precision. Accuracy in mathematical terms or statistical terms, bias is represented with an accuracy, and variability can be quantified, what you call it, a precision. If it is a smaller variation, it means it is more precise. Okay, so we broadly the variations that actually present in any process is divided into two reasons or two causes. So the one of the cause is what you call it a common cause or a random cause, or which doesn't have any particular reason which you can assign for the variation. Let's say you have some variable, and this variable you observe, let's say in the beginning you have certain behavior, so there is a spread and there is a central tendency. So once we follow that, it is central tendency remains the same, but from time to time it is the variations are very much the same as the previous variations. So in this further point of time, what we can do is the causes are common and they are random in nature. Some variable of interest is smaller, some are higher, and this is the central tendency. In future, variations can be predicted. So this is the essential feature of a common cause or a random cause, where you can predict if the process follows the same behavior as it has been observing in the past. So in the future also it is going to observe the same if the same randomness exists. So there is no assignable cause available for that variation. In contrast, if you see some special causes, if the process is changing drastically in terms of dispersion, is in terms of its how it is away from the mean value. So the shape of the distribution differs. For example, here very small variance, and here you can see a large variance, or here you can see this asymmetry exists. So if your process is having such a type of variations where there is a certain reason that could be assigned, or certain cause, we call it as some special cause. So in that case, this future variation in the process are not predictable. So there is always a question mark about the behavior of in terms of time, because once you observe this process and in future you cannot predict what will happen, because it is not the common cause, but it is a special cause. Okay, we will look into different types of special causes and the common causes. So common causes are actually sometimes called as natural variations or random variations. So that happens in the output of a process, and the reasons for all these variations could be many, but they are always minor in nature. For example, there are some general fluctuations, smaller level fluctuations occurs in the process, and the output varies, and mostly it is due to the chance or the randomness. So there is not a special cause associated. What we call it, a common cause is present, and these variations are statistically in control. It means you can predict them, they are stable, and they are predictable. And this variability is actually based upon the historical data that is available. So the ability to predict what the process variations are very much depending upon the historical experience. So these are the called as random variations or common cause variations. It could be few reasons in this production setup. For example, if your substandard raw material is coming to an input in the process, or if you have some measurement errors, or if you have some normal wear and tear, and your working conditions are not that up to the mark, and operators is not sufficiently trained, or the SOPs developed for a process are not appropriate, so that could bring those variation in the process, and your output is going to vary because of those common causes or random variations. In contrast, the non-random variations are actually the unnatural assignable variations in the output of a process. So in contrast to random variations, the non-random variations could be a big value, big variation, could be a variation in the mean as well as in the variance. And there are some special causes associated with that non-random variations, and the pattern is not predictable. There is always and this ability not to predict is just because of the fact that there are some special causes, and they are not predictable in the in this time process, and there is beyond the scope of the historical experience. The reasons, possible reasons could be that particular machine has some zero error, or there is certain malfunction associated, or let's say if operator is working and operator fall asleep, and the process got out of control, and big variations are coming in the process. Or it could be the poor adjustment of the equipment, or it could be some power surge where voltage fluctuates, increases or decreases, and which produces a big variation, or your controllers could be faulty. So depending upon the situation and the nature of the process, what material inputs are, what 6M are involved, and the output is going to have some larger variations. So they are called as non-random variations. And once you will go into this nomenclature of the control chart, you better understand what does it mean. So what is actually the control chart? Control chart is actually a time ordered plot of a sample statistics. So it means we are not actually investigating the whole population, but we are only taking a samples, and based on that sample observations, we are going to plot the sample statistics like the sample mean, the sample variance, range, or any other parameter depending upon the distribution. So if you plot those sample statistics with respect to the number of samples or with respect to the time or run after which you are inspecting or you're getting the samples you're investigating, and the good thing about control chart is once you plot that control chart, so you are able enough to distinguish between the different types of variabilities like random and non-random variabilities. So you can distinguish from the control chart whether the variation is due to the random nature or due to the common cause or due to some special cause, which is a non-random variability. So how the control chart looks like, for example, each sample is observed in the time order. For example, first sample is taken first, second sample is taken second. So the center line is actually called as a mean line. So if you are in this yellow region, it means the variations are in this normal variations or random variations. So these variations are taking place because of the inherent variations that exist. So the mean value, your observations for each sample would be somewhere hovering around the mean value. For example, this is slightly above the mean value, this is slightly lower the mean value, that is slightly above, just on the mean value, close to the mean value. So for every sample, your measurement, your sample statistic could be along the center, showing the central tendency of the data. So if you draw here the normal distribution curve, so there is a variation, 3 sigma variation on this side and 3 sigma variation on this side. So once your observation is crossing this normal region, where the variations are only due to this random effect, and that line, for example, this upper line is called upper control limit and this lower line is called lower control limit. So if your sample statistics is going to be not in this yellow region but outside the yellow region, we call that process to be out of control. And at the same time, obviously this out of control process occurs due to some abnormal variations, or there is certain reason associated. Maybe the operator has changed, or a new shift has come, or a machine has some electrical power surge which actually changed the mean value considerably. And in this normal range, everything is predictable and statistical. And once you are away from this normal variation range, what you call it, between the control limits, then it would be some special reasons for that variation. So so control charts can be thought of as a graphical tool for monitoring the activity of an ongoing process. It helps to track process statistics over time and to detect the presence of the special or assignable causes. It immediately gives great insight into short-term variations in the process as well, because depending upon which after how long you are taking the second sample and after how much time you are taking the third sample. So once you are doing the sampling, taking the samples in a shorter interval, then you can better have a resolution about predicting the variations. So this is generally, you can think of control charts to be a time ordered plot of statistical parameters, and if they are in the statistical confidence interval, we have already seen in that within this interval limits, then it would be called as the random variations or the variations due to chance. If anything happens which bring the process statistics out of that range, out of that interval, it would be due to some special causes. Okay, just take an example of here the ring diameter, average ring diameter is plotted on this y-axis and different samples are taking on the horizontal axis. So its lower control limit is this, upper control limit is this. So once we take different samples and we see most of the sample means are in this within the control limit. So that is something the process quite in control. So what control limits are? These are the lines between the random and the non-random deviations from the mean of the distribution. The center line is actually called as a mean which represent the central tendency of the data, and how much is this variation we can represent through either 3 sigma or 4 sigma or k times sigma, depending upon usually 99.7% of the area is coming into this region where the variation is due to the randomness, and the very small fraction goes out of the interval. So these control limits are the lines. If within this control limits, it would be the variations are random in nature, and if something happens across these limits, it would be due to certain special causes. As we have seen that from sampling distribution, that control limits are based on the sampling distribution. So larger value is actually called this upper control limit, and the lower value is called the lower control limit. And we have already seen that whatever your distribution is, it depends upon the distribution as well as your sampling strategy. For example, if your sample size is much smaller, then you have smaller variations in the sampling mean. If your sample mean becomes a sample, the statistic which you are plotting over the time or over different samples, it means that if the sample size is large, so you expect some smaller variation. So these control limits are being decided based upon the sample statistics and the criteria over which this area under the curve would be representing the probability. If the area under the curve between upper control limit and lower control limit is in 99.7%, so that would be representing almost the 3 sigma region. And if your process has a variation outside those control limits, so it could be, we can say it could be not due to this inherent randomness, but it is due to some special causes. Okay, the general theory about control chart, we already have seen the what is estimators, what are estimates, and point estimates as well as an interval estimates. We have already seen that. So for a general model, we just assume that theta cap is actually any sample statistic that measures some quality characteristics of the population parameter, which is theta. And let's say if its mean or expected value of that sample statistic would be represented as mu theta cap, it means that is actually representing the central tendency, or its variance or standard deviation of that sample statistic is represented by this is standard deviation. So standard deviation for this sample statistics theta cap. So whenever we put a cap over any letter, we always know that is from the some statistics that is coming from some sample. So the central line of the control chart can be so this expected value or mean value would be representing the center line. CL always use this for a center line, and UCL for upper control limits. So it means some mean value plus some k factor times the standard deviation of that sample estimator. or the lower control limit would be the mean value minus k times that sample estimator. So the difference is actually that variation which is due to the variations within this k sigma line. So the value of k is actually the number of standard deviations of the sample statistics, that is how much is varies from the mean value. Typically the value of k is chosen to be 3 for the normal distribution, where the area under the curve between the control limits would be 99.7%. So the very small fraction of it is probable to be out of control. Okay, so once we will go into these different types of control charts, so we better understand. But broadly speaking, control charts can be divided into two classes. What you call it, a variable charts and attribute charts. So variable means obviously where parameter is going to vary, and once it is a continuous variation, we call it a variable chart. Broadly, they are individual moving range chart, which we will not address in this course, but we will address the x bar. X bar is a mean and R is a range. So mean and range chart is to be studied, and mean and standard deviation chart to be studied. Once your subgroup sample size, we will talk about later, is less than 8, then it is intended to use this x bar range chart. If it is greater than 8, then if your sample size is individual, then individual moving range chart to be used. Once your sample size is greater than 8, then the variations are better explained through mean and standard deviation chart. S is the standard deviation, which is obviously we know that it is a sample standard deviation. So variable charts are used for such variables which are continuous in nature, and obviously there is certain distribution associated for those continuous random variables. Whereas in this control chart called attribute charts, so attribute is a particular characteristic of variable where you're using this p-value or proportion defective and C chart and U chart, which is actually the defects per unit. So C chart is once your sample size is fixed, we call it a C chart. If your sample size is varying, you call it a U chart. So where we are interested in how many defects per unit you are going to get, or in P chart you're interested in proportion defective. So there are some other charts like NP chart, and if you look at the sample statistics for continuous random variables are mean and range and standard deviations, whereas in attribute charts, which are for discrete random variables, you are dealing with binomial random variables where number of trials and probability of success NP is used. And in C chart, that is actually based on the Poisson distribution. So these are based on their distributions actually. Variable charts are based on continuous distributions. Attribute charts are based on the discrete distributions. So what is variable charts are used for continuous variables which can be measured. So both measure of central tendency, which is mean value, and the range and S are the variability to be used in these charts. Whereas in attribute charts, we are dealing with when you are counting the number of defective items per unit, whether or number of confirming or non-confirming parts you are going to produce in the process. So once you are dealing with such a process, we are going to use attribute charts. So once we will go into the detail, then we will learn what are other criteria for making a choice between variable charts and attribute charts. Okay, so we know the process is something which transforms certain input in an output, and this output at the feedback stage, there is certain measurement system which checks whether output is as per the requirement or not. So your measurement system is somewhat good enough to detect if there is certain special cause, or there should be a root cause of the problem. So you are able to identify why the variations are going to exist in the output, and it is not up to the specification. Or once you are able to identify it, then what you need is to do the corrective action. So once you perform the corrective action, then you just bring this whole change into the system so that your output becomes up to the mark. So this closed cycle always works, and the improvement in the process is actually the one of the advantage for working out these control charts. In production setup, most of the time we want to increase the productivity of our process. So productivity means more the output, lesser will with the same input. It means whatever the scrap work or the rework we have to do because of not coming to the standard and not meeting the specification and the requirement, so you are going to lose the productivity. So once you are developing control charts where your process is within this control, then obviously you are actually improving the productivity. So over the years people have learned that this control charts are the proven technique for improving productivity in production setups. Second, these control charts are act as some diagnostic tools where you have certain pattern recognition. So you can find out what are the reasons by which your process got out of control. So there is certain special cause associated, and in this developing this control chart for a process, we immediately recognize what are the reasons, what are the possible reasons for the variations in the process. Um the process control charts are effective in defect prevention by following a philosophy of do it right the first time. So whatever your system is, whatever 6 M's are involved in this production process, the intent is to reduce the number of defects. So in the first go you want to have the right product. So this strategy can be better judged through control charts. If you are doing the control charts, it means you are actually preventing the defects in your product. At the same time, prevent unnecessary process adjustments. So your process, this is actually a philosophy: if it is not broken, don't fix it. It means you don't need to revise your process unnecessarily, or you don't need to bring changes in the process such that your output is going to vary. So it doesn't mean that you should wait for the failure, but do not need to waste on putting, for example, if there's some random variations and the process is within the control limits, then you don't need to go for any changes. So because you are meeting the specification requirement. One of the benefits of the control chart is they actually help us in dealing with process capability. So just wait for a few more lectures to go into this statistical process control and process capability, where control charts are a very useful tool for investigating this process capability. So this is where I end this lecture.